part, Daniel already mentioned, the Onion URLs provide some kind of authentication. They are strong related to a specific hidden service, and that's what we don't want to lose because it's a feature. So if you have an Onion URL and you connect to this service, you can be sure, because the Tor network guarantees that you're really connected to this specific Onion, to this specific hidden service, and not somewhere else. That's what he said about phishing. It's not possible. Okay, let's see how we did this migration.
Okay, let's look behind the scenes of the migration now. We first have the onion key we mentioned. An onion key is a base 32 encoded hash of the hidden service public key. So we have the hidden service private key, and the public key is generated out of the private key, so it's the key pair, in fact. We calculate an SHA-1 hash out of the public key, or Tor does it, and now we have an 160-bit hash of it. 80 bits of this 160-bit we convert through base 32, and we get an onion address. This is how the onion addresses are created. So how do we come to the IPv6 addresses here? This is the IPv6 local address format. We have the prefix, we have the global ID subnet, and the interface ID. And we want to get the OnionCat addressing scheme. No. We just use the prefix, the global ID, and we have 48 bits for our new prefix for the OnionCat addressing. And the rest, the 16-bit subnet and the 64-bit interface ID, are the 80 bits of the hidden service key. Also, we can use now the hidden service key and put it into the 80 bits we get out of the subnet and the interface ID. So we just stripped out the subnet thing and pack everything inside it. So this is our new OnionCat locator, and this is the IP address we get out of this migration. And the best thing on it, it is definitely worldwide unique, and this provides the ability for automatic configuration as soon as you start OnionCat.
Okay, this IP address migration is the most important thing of all that stuff. On this is everything else based. The rest is just coding. Coding a piece of software which does the migration and... okay, so let's have a look what the coding stuff does. What does OnionCat internally? It opens a TON-top device. It then reads from the back end of the TON-top device through the kernel the IP packets which are coming in there through the routing table. Okay, then I read the IP header, I extract the destination IP address, then I can easily translate it to the .onion URL because the least significant 80 bits are in fact reflecting the Onion ID directly. With this information I can connect to Tor, to the SOCKS interface, and request a hidden service connection. Tor does this itself, and when it returns and says, okay, connection is open, let's forward packets. Okay, that's the last point here. I'm just forwarding packets to this connection, which has of course this IP address as destination address. Okay, that looks like the figure before, just with a little difference. There we have now 3 Tor proxies and 3 OnionCats. It's not limited to 3, of course, it can be 2 to the power of 80, of course, in theory, yeah, okay. So we have not anymore this SOCAT part here, we have OnionCat, that's SOCAT is the father of the name of OnionCat, of course. So that's OnionCat. OnionCat creates the TON-top device, it assigns the IP address itself. The IP address is determined from the local hidden service, which is configured here. And all the same stuff happens on the other OnionCats. So each OnionCat here is associated with a specific hidden service here, with a specific IP address for this hidden service. So if a packet comes in here, OnionCat does the translation stuff, connects through the hidden service here, and packets are forwarded to this And the rest does the kernel for us. We don't have to do anymore. The kernel receives packets and does with the packets as it does usual. Okay, let's look a bit into details of OnionCat. It's a multi-threaded application. The most important thing is there is a peer list. We keep track in this peer list of which hidden services are currently connected, which IP addresses are assigned to them, which Onion URLs and all that stuff. Then there are two main threads which are doing the data exchange, one on the receiving side and one on the sending side. Then there are two threads for accepting and accepting incoming and initiating outgoing connections. And last but not least, there are some supporting threads around. Okay. So the next picture shows you what OnionCat internally looks like. There on the one end we have the local operating system, Linux or whatever. On the other end, there is the Tor network. That means that's a Tor proxy, the local Tor proxy with the SOCKS interface, okay? So, and in between there sits OnionCat, and if we assume that connections are already established, as shown in the previous picture with the 3 OnionCats, packets arrive here from the local operating system. That's the tunnel receiver thread. It extracts the destination IP address, looks it up in the peer list, and forwards it to the Tor network. In the other end, there happens more or less the same thing, but we don't have to look up anything in the peer list. If packets receive from the Tor network, we just forward it to the TAN device, and then it gets to the kernel. That's all. Okay, let's see what happens if the connections are not established. There are two main threads involved in this. That's the SOCKS connector and the SOCKS socket acceptor. The SOCKS connector gets active if an IP address arrives on the tunnel end, which no peer is found in the peer list, which means there is no service, no connection to a hidden service already available. Then the tunnel receiver triggers this SOCKS connector. The SOCKS connector sends a SOCKS request to the Tor network connects, okay, and when the connect is okay, and when the connect is okay, we enter this to the peer list, this new peer, and packet forwarding can start. In the other end, there happens more or less the same thing. There is a socket acceptor. It's listening on the hidden services virtual, no, not on the virtual, on the real port here, of course. And if connections from someone else comes in here, Tor forwards it to the listening port here. The socket acceptor accepts this and enters the IP address in the peer list. There is a little problem here because we do not know the IP address of the other end, of course, because packets, the Tor network is based on TCP, so we just see more or less, we don't have IP information, so I have to receive one first initial packet that the socket acceptor can extract the originating address, the source address of an IP packet. So this entrance here in the peer list can done not before a single packet arrives there, but okay. Okay, that's more or less all that happens in OnionCat. So let's have a look at applications. What can we now do with this? Well, basically there are two applications we can think about. One is the traditional VPN use. We can just use it as a VPN across Tor. It's like OpenVPN. I think most of you know OpenVPN. It's a VPN like VPNs work. You can do the same thing with OnionCat, with the difference that you do not use the internet and traditional UDP. You use Tor as a transport for your data. And there's a nice feature in Tor, at least in the newer releases, or it's not releases, it's well before release, but you can download them. There is some kind of authorization built in hidden services, so you can supply your VPN users with a username and a password, more or less, that only connections happen to people knowing this password, okay? The application we thought about when creating OnionCat is that we want to build a Well, a global anonymous internet. If you don't have this authorization stuff, everybody can connect to everyone else with OnionCat through Tor. And because of the hidden service, they can't locate each other. They can exchange data, but they don't know where they are and who they are. So that's the major thing, the major application of what we think what OnionCat makes it useful. Okay. So if there is no authorization, you connect OnionCat as it is here, as it is currently configured. You got this unique IP address, and through this migration scheme we presented before, every OnionCat user, every OnionCat user can connect to every other OnionCat user. Well, and then what can you do with this? You can transport any kind of data you like. It can be UDP, it can IP, TCP, whatever. Okay. Well, yeah, there are some examples. You can mail, web, chat, IRC, be creative. Whatever you can do with IP. Okay.
One of the applications we also intended is that you can use regular DNS to memorize the IP addresses you have, because you couldn't, as we said before, you wouldn't be able to use a regular DNS for the onion keys. Yeah, the modes of operation. We got two modes of operation. The first mode of operation is the tune mode. It's based on layer 3. And the second is the tap mode, based on layer 2. The TUN mode is easier to use and intended for providing one or more services, but just on one machine. So there's no routing capability. You just have services on your machine, and OnionCat connects the services into the Tor network and into the hidden services. The tap mode is used for the total encapsulation of virtual machines. So if you plan to use, for example, VMware or another virtualization tool, you can provide virtual machines in there, and you can host services in there, and through the tap mode, the connection is routed into these machines. These operation modes are intransparent to the opposite OnionCats, so they don't know if the other end uses the tap or the tune mode. So this is just easy to use in this way.
Well, yes, that's an important point. I think if you have a TUN OnionCat on one end, you can have a tap OnionCat on the other end. They do not. That's what means intransparent. The other OnionCat does not see the layer 2 information, so it's completely layer 3 transparent, but not layer 2. And that was a little bit tricky in implementation, because the tap device actually is a layer 2 device, so I had to intercept the neighbor discovery protocol of the IPv6 to acknowledge the neighbor discoveries from the kernel. So that's the only part which is not transparent. Otherwise, it wouldn't work. Okay. The question was if you can set up the TUN mode with NUT on it. I'm not sure. As far as I know, there is no NUT defined for IPv6. But if you use IPv4, I'm not sure. I don't know if there is NUT available for IPv6. But of course, you can configure tunneling, IPv4 tunneling, through IPv6. This will, of course, forward through OnionCat, and on the IPv4 device, then you can apply NUT, of course. Okay, that's a simple application example about the tap device configuration. There, what you see here, the brown shaded figure is the host operating system, Linux or whatever. On this host operating system, you run the Tor and the OnionCat in tap mode, which means it provides a virtual tap device with all routing features tap devices have. And then what you next have here is, it's just an example, you run two virtual machines with VMware, VirtualBox, whatever. And all these virtualization techniques also provide usually some kind of network interface. And what you next do is you configure a virtual bridge here with, for example, the bridge tools. I tested it with Linux, it works perfect.